Good day to my respected teacher. I'm Nadia Naurin, and today I'll be giving a presentation on access control principles. So, in today's presentation, we will be discussing all this content in the upcoming slides. So, access control is one of the most important concepts in network security and cryptography. It's a technique that ensures only authorized access can access certain data or systems. Think of it like a digital security guard. It decides who can enter, what they can access, and what actions they're allowed to perform. For example, when you log into Instagram, your username and password make sure only you can access your account. Similarly, in government or business systems, access control helps protect sensitive data. Overall, it enforces the three pillars of security: confidentiality, integrity, and availability, commonly known as the CIA triad. The main purpose of access control is to manage who can access what. The first goal is to prevent unauthorized access to systems or data, meaning only legitimate users can get in. Next, it can ensure that authorized users can access data when needed, because locking everything down isn't helpful if the right people can't work. It also protects data integrity by making sure only specific users can modify information. Access control also supports accountability since all users' actions are logged, so if something goes wrong, it's traceable. And finally, it helps enforce organizational policies. For example, employees can only be able to access data relevant to the department. There are four basic components of access control. First, we have subjects. These are active entities like users or processes that request access to something. Second, objects. These are the passive entities like files, folders, or databases that hold information. Third, access rights. These define what type of operation is allowed, like read, write, or execute. And finally, access control policies. These are the rules that specify who gets what kind of access. In short, subjects act upon objects under certain rules and permissions. The access control process happens in four main steps. Identification. The user tells the system who they are, for example, by entering a username. Authentication. The user verifies the user's identity through passwords, one time codes, or biometrics. Authorization. Once verified, the system checks what the user is allowed to do based on defined policies. And the fourth is auditing. Finally, all actions are recorded and monitored to detect misuses. So if a hacker breaks in, the audit trail helps trace the sources of attack. And next we have, there are four major models that define how access control works. The first one is the discretionary access control DAC, mandatory access control MAC, role based access control RBAC, and attribute based access control ABAC. So each model suits a different purpose. Some give more flexibility while others often offer stricter control. In the next few slides, we'll look at each one of them in detail. In DAAC, access is based on the owner's discretion. The data owner decides who can access their files and what they can do with them. For example, in Windows, you can right click a file and choose who can read or edit it. That's DAC in action. This model is very common in personal computers and small organizations because it's simple to implement. However, it's also risky because users might accidentally give permissions to the wrong person, making it less secure in large systems. In MAC, access is strictly controlled by a central authority based on predefined policies. It uses security labels such as confidential, secret, and top secret. For example, in a military setting, someone with secret clearance cannot access top secret files. Here, users cannot change permissions on their own. Only the system administrator or the security policy decides. This makes MAC highly secure and ideal for environment like defense or government institutions, though it can be less flexible. In RBAC, permissions are assigned based on roles rather than individual. For instance, in a company, you might have roles like admin, manager, and employee. Each role comes with a specific set of permissions. When someone joins, they're assigned a role and they automatically inherit those permissions. It's efficient for large organizations because managing hundreds of employees becomes easy. If you change the permission of a role, it applies to everyone with that role. Hospitals are great example. Like doctors, nurses and receptionists each have different levels of access. ABAC takes access control to another level by using attributes like user characteristics, resource type, the time, location, or device. For example, a user might be allowed to access a system only during office hours and only from the company's Wi-Fi. It's flexible and context aware, making it suitable for cloud computing and IoT systems where conditions keep changing. So unlike RBAC, ABAC doesn't depend on predefined rules. Instead, it uses policies built on if then logic. The access control matrix is a table that shows which user can perform which action on which resource. Each row represents a user or each column represents a resource. The cell entries define what operations are allowed like read, write or print. For example, Alice may have read and print access to file A while Bob only has read access. In practice, systems often implement this concept through ACL access control or capability list to make the management more easier. In access control list or ACL is an implementation of the matrix. Here, each object such as file or database maintains a list of who can access it and how. For instance, in Linux systems like permissions are written like rwxr/xr showing who can read, write or execute. ACLs are simple, efficient and widely used in operating systems and firewalls. Capability lists work the opposite way of ACLs. Instead of each object keeping track of who can access it, each user or process keeps a list of what they're allowed to access. So a user's capability list might say file A read, file B write. So both ACLs and capability list achieve the same goal, mapping users to permissions, but they organize the data differently. Cryptography adds an extra layer of protection to access control. For example, encryption keys can serve as digital access tokens, ensuring only authorized users can decrypt and view information. Public key infrastructure, that is PKI, is used for user authentication, verifying digital identities. And digital signatures ensures integrity, meaning data hasn't been tampered with, and non-repudiation, and that means that the sender can't deny sending it. Together, cryptography and access control make system far more secure against cyber threats. Access control is everywhere in real life. In banking, in banking systems, different staff roles like tellers and managers have specific permissions. That's RBAC. In healthcare, doctors and nurses use ABAC access that depends on patient assignment and job roles. Cloud services use access control combined with multi-factor authentication to secure data, and even universities implement it. For example, students, staff, and administrators have different levels of system access. We interact with access control daily, often without realizing it. As networks grow, managing access control becomes more complex. There are five major challenges. So the first thing is managing large and complicated access policies, handling insider threats. That's the second one. And third one will be dealing with policy conflicts. Fourth one is adapting to cloud and IoT environment. And the fifth one is balancing usability with strong security. Organizations today are using AI based automation tool to simplify these tasks and to reduce human errors. So the future of access control is moving towards smarter adaptive systems. So one major concept is zero trust. The architecture, which means that never trust, always verify, even internal users are constantly re authenticated. We also have AI driven access decisions where machine learning can dynamically decide who should get access. Blockchain is being used for decentralized identity management and ensuring identities that can't be forged. And finally, continuous authentication, like monitoring a user's typing pattern or device behavior, will verify identity throughout a session. Now, to summarize access control in the blockchain of network security, we've seen how it protects data confidentiality, the integrity and availability using models like DAC, MAC, RBAC, and ABAC. With the integration of cryptographic techniques, systems have become stronger and more trustworthy. As technology evolves, access control is also becoming smarter with AI, zero trust models, and blockchain. It's truly one of the most critical defenses in cybersecurity today. And that's the end of my presentation. Thank you.